this. All right, done.
Okay. Now we can move on to our second talk. It is on non-equilibrium aspects of neutron star mergers, and it will be delivered by Nils Andersson. Nils is a professor at the University of Southampton, and he is an expert on neutron stars in general. Nils, I'll let you know when you have 5 minutes left before the questions.
Thank you. And Rahima is a student of mine and Ian's, so that was awkward for you. All right, well, thank you all for having me, and thanks particularly to Tim for covering exactly all the aspects I'm not going to talk about. So in this short talk, I'm going to focus on the physics of non-equilibrium, neutron star matter. I'm going to try to give you an idea of why we will struggle probably to deal with some of these things. Not to be too negative, but also that there is need not just to improve the numerics and the simulations, but the physics that goes in and how we deal with those aspects of physics. That's the sort of scope that I want to try to get across. So let me start where Tim started, more or less, which is that with at the moment we've seen a few neutron star binary mergers, maybe a couple or a few black hole neutron star mergers. For those of us that are obsessed with extreme density matter, we want to see more. We want to see higher signal to noise events and so on. We will need next generation's instruments like Cosmic Explorer, Einstein Telescope to do this. And I guess we'll have to hope that the event rate does not keep on going down the way it seems now with O4, but let's not be too negative. One question that is quite natural from the sort of theory side where I come from is that how much of the neutron star physics can we expect to extract from high signal to noise signals? So that would be in the next generation era. Now, the obvious thing you will need, which is clearly demonstrated by Tim's talk, is you need a reliable and robust numerical simulations at very high accuracy with a faithful implementation of the physics. And so I'm going to focus on non-equilibrium aspects of neutron star physics, just to give you a flavor of what I think is not currently dealt with as at the level we need. But I think one should also make the point that if you do the simple sort of waveform mismatch argument, how accurate a waveform needs to be able to be distinguishable, or two waveforms to be distinguishable in the next generation era, then I think it's fair to say, and I think that was kind of Tim's message as well, that current neutron star simulations are nowhere near where they would need to be. So that's one problem. The other problem was also touched on by Tim, which is that we will never, in my opinion, unless we run simulations for these centuries that he alluded to, I'm a little bit too old to do that, so we're not going to go that way. We will never be in a position where we will build sort of waveform surrogate models like you can do for black holes, because we can't afford to do large enough numbers of simulations of the required accuracy. So we need to be, again, I think that was stated at the end of Tim's talk, we need to come up with new approaches somehow. We need to get this done because we need to cover parameter space and so on. So one thing that I'm interested in is the systematics. So I think that whilst it is true that we don't need to worry too much about systematic errors in simulations today, I think we will be hit by systematics when we go across the threshold to the next generation. So that's what I'm interested in, the different kinds of systematics. And so today, my main interest is in physics systematics. And by that, I mean, it could be physics that is not included in the simulation, or physics that is not, let's call it, correctly included in the simulation. So that's what I want to talk about. So let me start summarizing my view of what is going on, a little bit like Tim's slide with all the waveform models, but I didn't give things name because I don't think they have names the same way. But the typical standard state-of-the-art numerical relativity simulation builds on tabulated 3-parameter equations of state. So you say work at tables of number density, energy density, electron fraction, or some lepton fraction, And then you simulate this, obviously at each time step inverting using some conservative to primitive approach and so on, back to the sort of physics variables. And then I think you can classify simulations in basically 3 different categories, 2 of which assume that the matter is in equilibrium. So I want to spend a little bit of time on that. And others say, well, we're going to go beyond equilibrium and add some more physics. Okay, so old school would be to say, forget about fancy things like temperature, etc. Simplify the equation of state, get rid of the lepton fraction, more or less, because matter is in beta equilibrium. So you can write this as a barotrope, simulate all you like, but you can't cover what happens when you get shock heating and so on. And I think that's a very important part of the simulation technology, because this is what you have to do, I would argue, if you want to build in-spiral waveform models like Tim does. So what you're doing then is you're basically assuming that all nuclear reactions, etc., are fast enough that the matter is in beta equilibrium. Now, is that true? Well, we'll see in a minute. Or the alternative is that you say, well, either reactions are really fast or they are in fact very, very slow. If reactions are very slow, then it doesn't matter what happens. The fluid moves about a bit, but it retains its identity. So if you move along with the fluid, each fluid element, it keeps, say, the lepton fraction that it had at the beginning. So the composition is frozen. Now, if you work in those 2 limits, the fast and slow, then we can quite easily use current tabulated data and just simulate. Now, the underlying question in this statement is, what do I mean by equilibrium? And that's what I want to sort of argue, that we're not clear enough on that. And that's actually quite a difficult question. Then, of course, state-of-the-art simulations that are not focused on in-spiral, but rather, post-merger, recognize that you need to do more. We're missing physics. And so we need to include, say, nuclear reactions and neutrino emission, which is difficult, right? So I'm not going to talk much about that. We need some kind of closure scheme, either a moment closure or some actual full Boltzmann, which I don't even want to think about. And as we heard the other day from Carlos, we want to add MHD because ultimately we want to model multi-messenger astrophysics. So we want to model kilonova emission and jets. And so for the jets emission, clearly MHD is going to be important. Now, I think some of the key aspects were covered already by Carlos. So I'm not going to talk about MHD, although I will be talking a bit about the large eddy kind of thing and aspects that come in when you start thinking about large eddy filtering and things like that. Okay? So this is setting the scene for where I'm going. So I want to spend a few minutes just on something very, very basic, namely, how do we go from sort of matter description down to these equilibrium statements? And then I want to ask myself, is any of these assumptions actually true in the neutron star merger? And probably the answer is no, and then I can just close and go home. So typically, of course, we assume that we simulate the first instance, a perfect fluid without viscosity and so on, because if we have viscosity, then we end up with all these issues of how we represent viscosity with Israel Stewart or some other BDNK formalism perhaps, but I don't want to start there. So I have a perfect fluid stress energy tensor, energy density, and pressure as usual. Now, clearly, we need to close this with an equation of state. We had to talk about the equations of state the other day. There are many popular choices, but actually not that many that are used in simulations, because as anyone that's run a simulation with a realistic equation of state would know, is not quite straightforward to switch from one model to another. There's always some tweaking going on with the equation of state table. It's not just, plug and play. So one needs to be a little bit careful there. But the equation of state is the thing that carries all the microphysics. Now, the key point I want to stress here is the equation of state is calculated from some nuclear model, QCD, whatever approximation, but it's calculated on a very, very minuscule scale compared to where we're simulating, right? The nuclear scale is like the hundreds of Fermi, right? Whereas the simulation scale is, let's be generous, tens of meters, right? If we're more realistic, it's hundreds of meters. So there are a few orders of magnitude in between a few hundred Fermi and tens of meters. And a lot of things can happen to the physics if you average and extrapolate on those scales. And that, I think, is really important for us to try to understand better as we go forward. Okay, so how does this argument go? Well, if you start with a single fluid, say nuclear matter, neutrons, protons, electrons, so NP and E, you have a sort of Gibbs relation, the first law of thermodynamics that says pressure and energy adds up to number densities and chemical potentials multiplied, add them up. This is a relation that has to hold thermodynamically. And then what you do is you say, well, okay, I don't want to do MHD because Carlos is doing that. So I'm going to assume that the matter is charge neutral. If it's not, then I'm in trouble. I would have to account for charge currents. Now, charge neutrality is an absolute requirement on the nuclear scale, so on the small scale. All equations of state are charge neutral. End of story. But the question is, if this holds when you average up to this larger scale, I believe the answer is no. And then you're in slight trouble. And I'm going to tell you why later the answer is most likely no. But anyway, let's go with this. Then you introduce typically the baryon number density, because who cares about neutrons and protons being different? So you lump those together, and that brings in then the lepton fraction, because you divide electron number density with baryon number density to get a fraction as a key parameter. But that's just the definition, so that should be okay. And then you say, well, I know beta equilibrium is chemical potential balance between neutrons on the one hand, protons and electrons on the other hand, ignoring neutrinos. So I rearrange this with that in mind, and then I end up saying, if the matter is in equilibrium, I just get a single parameter, the baryon number density, and a single chemical potential. I've simplified the problem. It's now a barotropic model, and everything is fine, and I'm happy. Okay? So the 2 points then I raised already, charge neutrality is dubious, perhaps, on the larger scale, and the equilibrium. So the question then is this statement of beta equilibrium true? Is this what I should be using? If the answer is no, then clearly this reduction is problematic, and I need to keep track of the chemical potential differences and maybe reactions, and life gets much harder. So let's have a look at this. So I've used some old images from a paper with Pete Hammond from years ago because I think they illustrate this very well. So what we've done here is we said, let's quantify this deviation from cold beta equilibrium in a simulation. So this is just a vanilla, very simplistic neutron star merger with APR, I think. And so you see at merger in the left panel, the shock heating, which you expect, which ramps up this difference in chemical potential, which cunningly in the figure is called mu delta, but in my slide is called beta, so that's very professional. And on the right, you see later how you have two hotspots that sort of rotate around where you're vastly out of equilibrium and so on. So this illustrates, I think, the amount of deviation from chemical equilibrium you should expect in a typical neutron star merger simulation. And clearly, you're not actually very close to equilibrium at all, in parts of your domain. Whereas there are other parts where you are, you're fine. So, of course, this simulation is done assuming imposing equilibrium and then quantifying, where the matter wants to be. So it's a bit of a cheat, right? So the point I want to make here is this, right? I can make a statement about this cold beta equilibrium because it relies only on the equation of state table. I can make a statement about frozen composition because this involves simply tracking where the leptons go in my simulation. That's fine. But if I wanted to impose a real equilibrium of this matter, which ramps up to some, nearly 100 MeV in places, I might need to be more careful. And there are two caveats here. The first one is the notion that's been around for a couple of years from Alex Haber and Mark Alford that equilibrium at up to, say, something like 10 MeV is quite different from the cold equilibrium, because the forwards and backwards Oerker reactions progress at a different rate. And that means that this condition I stated for equilibrium is not the correct condition to impose. And so we think, based on calculations that have been done, that leads to a softening of matter in regions where the temperature is up to 10 MeV. But this has never been modeled in any simulations because we don't have a tabulated equation of state to use. So then you can say, well, that's not our problem. That's the nuclear physics guys that are not providing the input. But, this is a dialogue that I think we might need to improve. The other thing that's important is we all know that the beta equilibrium statement changes completely if we incorporate neutrinos, because then we need to put in a neutrino chemical potential. And if the neutrinos are trapped, so their mean free path is short enough that they stay in the matter part, then this changes completely. And so that's important. We know that's important. That's why people are trying to put in neutrino aspects, right? But this is also really tricky because the neutrinos, there's not just one stated mean free path for the neutrinos. This is a frequency or energy dependent statement. So you may have part of some neutrinos in your simulation that are trapped and some neutrinos that are not trapped, and you need to somehow keep track of this. And at that point, I think that's above my pay grade, and I'm just not going to touch that. But I think the point here is, as we ramp up the temperature, the notion of equilibrium changes, and we need to pay attention to this. And I think that just adds to what Tim said about the general mess that is post-merger physics. You might not choose not to worry about this, but if we think at some point in the future we're going to be studying actual neutron star physics with post-merger signals, I think we need to think about these things. So that's a long rant about this. So this is just another slide from Pete saying where in the sort of chemical potential temperature phase diagram or the matter in these simulations. I'm not going to touch on this, so let's just move on. I want to make one more point about finite temperature simulations and mergers. I think we all know, we collectively, people that have ever looked at the finite temperature simulation and asked themselves, what is the temperature in the merger? We all know that the temperature is, quote, wrong. And we know that because if you look at the left panel here, where the dark left panel of the left panel, if you like, is temperature, you see that there's a purple sort of, halo around the neutron star at merger. And in that purple halo, the temperature is order 10 MeV, I think, give or take 10, 15 MeV. Now, when neutron stars in spiral, they're cold. They should be 0.01 MeV or something, or 1 keV, something like that, right? And that's clearly not the case. So from the beginning of the simulation, the shock heating just ramps up the temperature at the surface, which impact actually then filters through the entire matter domain, and the temperature is just wrong. Tough luck. Now, I could say, well, I don't really care about this because I'm not like Tim. I'm not interested in spirals. I'm focused entirely on mergers, and I know the temperature in merger on the right is much higher. So this 10 MeV, whatever, that's nothing to me, right? So ignore. But if you ask yourself, what would this 10 MeV do to things like the tidal deformability and so on in my simulation? I'm afraid the answer is that answer will now also be wrong. And so I would be worried about this in the sense that I cannot use the state-of-the-art simulations aimed at merger physics to match with the state-of-the-art simulations aimed at in-spiral and waveform modeling. And I think that's a little bit unsatisfactory, right? Clearly. We wouldn't have one set of simulations that, rules them all, like the Lord of the Rings kind of situation, right? So I think this is a real problem. I understand we struggle with this, the surface shock heating, right? I totally appreciate that. But I think it is an important problem to think about if we're interested in more the sort of technical developments. Okay, so let me talk a little bit about reactions. So if we want to study nuclear reactions, so the deviations from equilibrium and how the neutron star matter retains or moves back towards equilibrium, then basically there are two aspects of this. We need to keep track of the lepton fraction, so that's some advection here, with some rates. And so the problems here then are basically summarized like this. If the reactions are slow, so that they happen on a time scale that we're resolving, then clearly we just put the reactions in the simulation, we resolve them, and we evolve the full system, right? No problem. Oh, but I say no problem. This, might be very stiff or whatever, but in theory, no problem. And as a theorist, I can say things like that, right? I'll say to Rahima, as a student, Rahima, go and simulate this, and she just goes away and never comes back. On the other hand, if reactions are fast, so I can't resolve them, I can either decide not to worry about them, say, well, I'm now back in this equilibrium situation, or I can say, well, it's possible that they are still doing something. There could be some aspect of, say, bulk viscosity, right, that enters into this, and I might worry about this. So then I can add some approximation that says I'm adding viscosity to my simulation, and that will sort out this problem. Now, the problem is this. In a typical neutron star simulation, and that's the argument I want to make, we are both in case 1 and in case 2, which means that we need to figure out what happens in between, or conversely, what happens if I add in a bulk viscosity to a simulation where I partly resolve reactions, or vice versa. And I don't think we have any control over this at the moment at all. It leads to an element of sort of double counting that I would be quite worried about. So this, I think, is a really difficult problem. So timescales, well, merger dynamics on milliseconds, typical numerical resolution, maybe 10 to the -7 to -8 seconds, ERCA reactions, standard ERCA, a little bit, faster, perhaps. So I'm not going to talk about the simulation. Let's just talk about what would happen if I decided that there are some reactions that are too fast for me to resolve. So I want to put in an approximation, right? So the typical approximation you would do in dissipative hydrodynamics is you expand with respect to your equilibrium, which of course means that you're suggesting that you know what equilibrium means, which you might not, as I've just said, but let's not worry about that. And so you do this expansion, is a Taylor expansion. So you end up with something like this figure here from a paper with Thomas Celora, also a little while ago. So the typical thing you do is you end up with bulk viscous pressure that you add to your equations, and you think everything is fine. So this illustration is aimed at showing the following. The real bulk viscosity has a resonant peak, that's that round dot in the middle, and so at very low frequencies towards the left, it's a straight line that rises. At very high frequencies on the right, it tapers off again. You're off resonance, okay? And now I'm imagining the following. I'm having a numerical resolution box that resolves some frequencies, but not all of them, okay? And I can slide that gray box across, okay? If I slide that very far to the left, then a linear approximation to this blue curve, so the orange curve, orange line, is good, right? And if the gray but unresolved bit covers everything else, then I'm in business. This is a good approximation, right? But if I slide this gray resolution box over to the right so that I uncover this resonant peak, so that where the blue curve turns over, then clearly my orange approximation becomes increasingly worse. And I'm now overcounting what I should be doing. And so now imagine what happens if I try to put in reactions on the one hand, and also say there's some dissipation in this, then it's even worse, because now I'm double counting. And so I think this is a problem that we need to figure out. If it is the case that some parts of our domains are resolved, and some of them are not, and we start playing with non-equilibrium physics. This is not straightforward, I think. So I don't even have an idea for this. So here's some, again, from this paper with Thomas, just to tell you roughly where I think we are. So this shows, again, the temperature density phase space shows roughly the timescales we're talking about. So this here is the typical reaction timescales calculated for, again, APR, I think, with contours indicating the typical timescales of resolution. So if you can go to the very top, it's kind of an estimate of where we might be some 10 years from now. So say we do an order of magnitude better in resolution. The key point here then is the timescales you need are similar to the reaction timescales. So we will be getting closer, but at the top right-hand corner, there will still be things we don't resolve, whereas you go down in the temperature scale, forget about the left bit here, just go to the very right and go straight down. In temperature, there will always be bits where we now can resolve reactions, but there are parts where we can't. So we are in this gray area that I talked about. Is it important? So this is an estimate of how important bulk viscosity is with the same temperature timescale contours. So if you go on the very right, I said the upper right corner is important. If you then go above the dotted line on the right corner and you ask how big is this effect, and you look at the color chart in the bar on the right, you'll see that we're talking about percent level effects, which you would say, I don't really care about percent level effects, which would be fair enough. But if you go to a nuclear physicist and you tell them that you don't care about percent level effects in the nuclear physics, they're going to throw you out. And so, you might not care about that either, but they will be unhappy. Okay, so I'm going to close with a few comments on turbulence and large eddy modeling. So this is something we've been very interested in the last couple of years, but from the sort of theory side. So I will talk a little bit about that and why I think this is also very important, even if we're not doing MHD. So Carlos talked about this for magnetic field evolution and saturation and so on in dynamos. I want to talk about the fluid aspects. So the problem is the one I said, right? We have a mean free path or something in the neutron star core of a fraction of a millimeter, similar to the dissipation scale. And then we have the best resolutions, which are 10 to 100 to several hundred meters, right? So if there is physics that we cannot represent in the simulation, but yet is important, like turbulence, we need a trick for representing this physics. And the standard go-to tool is large eddy filtering, right? The challenge we have, I think, is twofold. Nobody knows how to do this in general relativity proper. And we also have the problem that we do the simulations and in a frame that's not co-moving with the fluids. So we always have to use a conservative to primitive step, right? And so that says you need to think very carefully about whether you do this large eddy closure thing in the foliation or in the fibration where the fluid moves, right? And so we've given this some thought, and we would argue that if you want to do this the right way as a theorist, and you want to enforce the covariance of general relativity, right, then the natural way to do this is always to do the filtering and anything like that in a frame tied to the fluids, in the fibration, not in the foliation. Now that you can define, it's compatible with the theory, that's fine. There's an explicit link to the thermodynamics. Everything is really beautiful, but this is not where you're evolving the equations. And this scheme that we're working on, I think, is not available for simulations, or will not be available for actual simulations on the human timescale. But let's not worry too much about that. This is a theory exercise, okay? But I think we're learning really useful things from this. So that's what I wanted to close with. So here is a very, very simple argument, and this is maybe the key take-home message for this, right? Whenever you filter an ideal fluid, so this is my ideal fluid stress energy tensor again, basically everything that is nonlinear, so the energy density times the velocities UA, UB, whatever, for example, anything that includes a nonlinear term will need a filter closure to be modeled, right? And so that's quite simple. And then it's very easy to realize that if you filter the ideal fluid stress energy tensor, you always end up with a non-ideal stress energy tensor. So the filtered version of, standard ideal fluid dynamics is dissipative fluid dynamics. There's no way around it. And that means, as a point that was also made by Carlos, that because we're doing finite differencing, which is effectively filtering, we are always, we don't know it, but we're always de facto simulating dissipative fluid dynamics, right? So you might say, okay, I don't care about this because I'm going to increase my convergence until everything is gone and I don't worry about this. And that assumes that you can do this, right? That you can keep on increasing resolution until you're happy. I'm not convinced that we're going to get there. And so I'm going to park this as an issue. So anyway, suppose I do this modeling and come up with some closure scheme. Now, there is another warning here, which is the thermodynamics. Now, I wrote down the Gibbs relation for a barotropic model where I just had a number density and a chemical potential on the right-hand side. Now, that's a product, so that's a nonlinear term, which means that if I now filter this, I will pick up an extra bit, right? And so in my LES scheme, the equation of state that I need to simulate is not ever going to be the equation of state that's given to me by nuclear physics. Or to be, more provocative, in a finite difference simulation, I am never, ever simulating the equation of state that is given to me in the table. And so if you're worried about words like systematic errors, this is an obvious warning that we need to understand better how the systematics enters through the physics, or vice versa, what is the effect of the systematics is on the physics. So I think that's if we're going into a very high precision era with gravitational waves, that's something I would be worried on. So I think I've outstayed my welcome, absolutely. So I'm going to leave you with this take-home message. So I think it's clear that when in the next decade, provided we get the money to do this, next generation instruments are really going to provide us with the tools to use observations to test neutron star theory at a level we can't even imagine today. This will need serious improvements, I think, in the models. The waveform models for in-spiral that Tim talked about, we know how much we have to push. And the post-merger, I think, is kind of, more physics and also difficult, right? I believe on the sort of crossover with theory and not just actual simulations. I think the non-equilibrium aspects are where we need to push. They're clearly going to be difficult to implement in simulations, and we need to pay attention to this, not double counting and so on. It's not just a numerical issue. There is a theoretical problem here that we need to figure out. I think inevitably we will need to start thinking about turbulence and some large eddy schemes. We need to figure out what averaging and filtering does to simulations and how this leads to systematics that perhaps we didn't worry about, right? And that's pretty much it. Thank you very much for putting up with me. I'm done. So there you go.
Thank you very much, Nils, for the very nice talk.